because the first thing is to get it into this form if it's not. The second thing is we are going to find an integrating factor. So often we call it mu, but sometimes you'll see other letters like rho or something like that. But the key thing is you're finding an integrating factor. Integration factor. I'm going to call it integrating. Forgot. Integrating factor. So mu of x is going to be e to the integral of p of x dx. And it kind of looks random why we're doing this, but it's really cool when it all comes together. So we'll see here as we build the intuition. So in this case, this p of x is this p of x, which we said was 3. So remember, it's p of x y, because, you know, it might not look like 3y is a function of x, which it's not, but we have this y here. So the p of x in this question is just 3. But in theory, you know, we could have 3x squared y or something like that, and our p of x would be 3x squared, and then this y lines up. So in this case, our p of x is 3. So we do e to the integral of 3 dx. The integral of 3 with respect to x is just 3x, right? The derivative of 3x is 3. And we don't need to add z or anything here because we still have more work to do. So our integrating factor is e to the 3x. E to the 3x. So then the next step then is to multiply both sides by e to the 3x. So multiply by e to the 3x. I guess I should say like the whole equation, like this whole equation, but hopefully you can follow along here. So we have both sides, so e to the 3x dy dx plus 3 e to the 3x y equals 6x e to the 3x. Does that make sense? I'm multiplying both sides of this equation by e to the 3x, and because I'm multiplying this whole part, I have to distribute that, and so we're basically multiplying by e to the 3x, like each of these terms by e to the 3x. So e to the 3x times this plus, and then I'm just putting the e to the 3x in between here, but it's 3 e to the 3x y equals 6x e to the 3x. Now right now it kind of looks random, but the reason we do this is because so now we can actually see. It's a little tricky at first, but when you do this over and over, you'll kind of start to see this pattern. The reason we did that is because if we look at this side, this is actually the product, the derivative of a product. And so it's the derivative of, let me write it out, the derivative of d of e to the 3xy this is the derivative of e to the 3x, and you keep your y plus, and then you keep your e to the 3x, and you take the derivative of y. It's a lot to say out loud, but if you want to confirm this, do take your time here, but that's actually kind of the point of multiplying through by this integrating factor. So we can simplify this whole part now into this, and then the other side is still 6x e to the 3x. So now we're just going to go ahead and take the integral, right? We're going to try and take the integral of this so that we can get e to the 3xy equals the integral of the other side, which is just a function of x now. So it's 6x e to the 3x dx. Okay, that's very good. So now we can just do this integral. However, it's just a single variable integral, all with respect to x. There's no y anymore, so that's kind of nice. So we can do this however we can. Okay, so we were left with e to the 3xy, which was the d of this dy, the product rule, right? But we're going to take the integral of this part, so that's why the this dy went away, because we're just going to go ahead and do the integral. And on this side, we have just a function of x here, so this is just a regular calculus integral, right, with the single variable, just x, which is important because that's why it was important for our form to have q of x over here, because once we multiplied by the integrating factor, this is all in terms of x, so we can actually solve this. So I have a linear term multiplied by an exponential term, so that screams integration by parts to me. There's no real, and especially because in this case we don't have like a u substitution or anything. I guess not screams, there's no screaming in ASMR, but it gently whispers to me that this will be integration by parts. So let's go ahead and actually find this integral. We are, just for review, wanting one piece to be u, which we're going to take the derivative of, and another part of this to be dv, which we're going to take the integral of, to use our integration by parts formula. So I'm going to go ahead and let u equal 6x. Since you have an exponential, like e to the x or something, both the derivative and the integral is e to the x, and we do a little u substitution here or some chain rule, but it has the same form, so it doesn't simplify anything when we take the derivative versus the integral. But if we look at the 6x term, when we take the derivative, it becomes a constant. So technically you can pull the 6 out first and then just work with the x, but it doesn't really matter. I'll just keep it here. So in this case, I'm going to let 6x be my u part, and e to the 3x dx be my dv part for my integration by parts. And from these choices, I calculate du, which is 6 here. The derivative of 6x is just a 6. And the integral of dv equals this is going to be, we have a 3x up here, so if it were 3 to the x, the integral is just e to the x, so e to the 3x, but we can do a little u substitution, because when you're doing kind of the antiderivative, you're going to end up doing the chain rule, right, and you'd have to multiply by 3 in front, so instead I'm going to divide by 3. You can write out the steps if you want to, but this is just the idea. You can confirm that the derivative of this is this, because when you take the derivative of this, the derivative of e to the 3x is e to the 3x times 3 for your chain rule, and then this 3 cancels out with that. So anyway, hopefully this part is okay, or we can, you can go back and review integration by parts, but this is our integral of what just happened? Well, we did e to the 3xy, we did this integral, so this is actually just regular calculus review. And so now we can divide by e to the 3x through this and get our y. So y is going to equal 2x. So the e to the 3x terms cancel, minus 2/3. And then plus c, and I'm going to just go ahead and write it as e to the negative 3x, right? Or you can do c over e to the 3x. And that's it. But now we're given that y of 0 equals 1. So in general, this would be our general form for our solution. But because we're given y of 0 equals 1 in our initial condition, we'll actually solve what this c is. So when x is 0, y is 1. So I'm going to go plug in this initial condition. So when x is 0, y is 1. So 1 will equal 0 minus 2/3 plus c e to the 0. So anything to the 0, and e is some constant. So not some constant, a special constant, but it's a constant. E to the 0 is 1. So just c here. So c is going to equal 1 plus 2/3, which is 3 over 3 plus 2 over 3. So 5/3. So our function, our final answer, should be that y equals 5/3 e to the negative 3x plus 2x minus 2/3. And I am genuinely hoping that we didn't mess up anywhere, because I have no idea what the actual answer is. But the nice thing is that we can always come back and check. So theoretically, if we didn't mess up anywhere, this is our function of x that satisfies this initial value. So theoretically, the derivative of this thing plus 3 times this thing should clean up to equal 6x. So dare we check that? Yes, I think so. I think it will be satisfying to do, and if it works out, and if it doesn't work out, then you won't be watching this video right now. Okay, so here's our original equation with the initial value, and this was the answer that we got that we're about to check. And this is actually, I thought it was cool, it's in the rainbow section, so I'm just gonna leave it here, and we're just gonna do all of our checking up here. Okay, so again, we were looking for y as a function of x, which is, for starters, what we got. We have y equals, and this involves only x. Okay, so that's a good start. Next, I'm just going to go ahead and quickly double check this initial condition, because I don't want to do all this work if this isn't even quite right. So y of 0 is 5/3 e to the 0. Negative 3 times 0 is 0, so e to the 0 plus 2 times 0 minus 2/3. So this will go away. E to the 0 is 1. So we have 5/3 minus 2/3, which is 3 over 3, which is 1. So good. That part is fine. Okay, so now we have to do dy dx. We're taking the derivative of this. So the derivative of e to the negative 3x is negative 3e to the negative 3x. So I'm not going to write every single part here, but hopefully you're comfortable with the chain rule. If not, definitely take your time. But this cancel, and we're left with 6x. Oh, phew. Okay, so no calculation issues. So it looks kind of messy, but all these terms end up canceling out. So just to be clear, this part, this first parentheses part, is the dy dx, and then this part is just 3y, and so we still have the plus here, and that equals 6x. So that checks out. So that is a relief, and I'm glad that it does. And that's the nice part about differential equations, is it might get messy, but you can kind of check your answers. I find that rather satisfying. So this is just one of the techniques that you might learn in a DiffEQ class. It is important to try to classify what type of question you're looking at, because these are just all general techniques, right? Any just differential equation in general is literally just an equation that involves derivatives. So depending on your actual situation, you might learn these different ways of solving them. And so, for instance, separable equations, or then you have, of course, second order, and other techniques too. So this is for first order linear ODEs. You work with this integrating factor, and you can actually kind of do the mental exercise of generalizing. If you have this dy dx plus, p of xy equals q of x, you can kind of look at why you have this integrating factor, kind of build some general intuition behind why it ends up being d of that product dx, and why that actually simplifies things. It's kind of good to do in general, but as you do these problems, you can kind of see, like how we had it before. We had d of, e to the negative 3x times y, right? That's kind of the whole point of finding this integrating factor and multiplying it across the whole equation, so that you can kind of combine these parts here, because you have